Speak to you today. Today I want to talk about, my title was Dark Matter Halo Density Profiles, but I'm going to narrow in a little bit and talk about one specific thing. And so what I decided to talk about is a new mass estimator for dispersion-supported galaxies that's based on velocities of stars in the plane of the sky. And so this is relevant, we hope, in the era of Gaia in particular, where we're sort of entering into an era where it's going to be possible to not measure line-of-sight velocity dispersions for dwarf galaxies, but to measure velocity dispersions of dwarf galaxies in the plane of the sky. And it's specifically a specific mass estimator that works at one radius in a galaxy, and it's a different radius than it works for line-of-sight velocity dispersions. The context being this might be a way towards measuring density profile slopes quickly and easily from data sets without doing complicated genes modeling. So this is work primarily done by Alexandre Lazar, who's a fairly young graduate student at UC Irvine. So the context of this, I talked about it before. We all know about the core cusp problem. It goes back to the early 90s, Flores and Premack. So we're sort of here at the birth of this problem, which won't go away it could be observational, it could be a theoretical issue. But let's just pretend that we all know that there are cores in some galaxies and that it's not an observational issue for now. And soon after that, it was pretty quick that people realized that in principle feedback could solve this problem. So if you throw out a lot of gas and you kick around the dark matter particles in some way by changing the force that they're orbiting on, you can change the orbits of those dark matter particles and create something that looks more like a core than a cusp. This has been something people have known for quite a long time. We've been looking at this issue in the fire simulations. I'll just quickly advertise this as sort of setup, looking at sort of a big suite of Fire 2 simulations, more than 50 galaxies, all of which are resolved to less than 0.5% of the virial radius, and measuring what the density profiles look like in things going from ultra-faint systems all the way to the Milky Way. And what's interesting is cores are created in these systems. This is seen by lots of other people, but sort of in fire, this is what it looks like. One of the things that's kind of interesting is we're able to actually fit all of the cored hydro simulations with a profile shape that's basically an inosto with a softening term in it. So it's like the normal inosto profile, and you just stick a core radius in, and it works incredibly well, actually. In fact, so with one extra free parameter, it actually works as well as inosto does for the dark matter only simulations. So this is kind of fun for us. It was kind of fun for us to see, and in this paper we'll provide fitting functions and stuff like that. But it's quite interesting. But one thing I want to focus on here is as you go from ultra faint to classical to bright dwarf, sort of big LMCs, and then all the way to the Milky Way, you go from systems that basically don't form enough stars to make a core to sort of the bright dwarf range where it's really efficient to make cores. And then you go to the Milky Way, and actually you get two things going on. You get some baryonic contraction, so the system is actually denser than dark matter only simulations, but there's still a small core in there. So you get kind of a couple things going on at the Milky Way scale, which is interesting. This is a comparison to lots of other work that's been done, and there are many people. We saw Jonathan's talk earlier about understanding the physics of what drives this. But I like this plot because it shows a lot of similarities between different models who kind of qualitatively agree on this same picture, going back to Decentio, who made this plot the first time, which is basically you plot the log slope of the density profile at roughly the half-light radius of a galaxy as a function of the ratio of stellar mass to halo mass. And there's sort of this sweet spot. If you're up high on this thing, you've got a core. If you're down low, you've got a cusp. And there's kind of this sweet spot right around bright dwarfs where most of the simulations predict pretty big cores. At least this class of kind of sporadic feedback simulations predict these more core-like systems. But then by the time you get down to dwarf galaxies, basically nobody's predicting the existence of cores, and everybody's still making cusps. In detail, we actually find different shapes in them. We're finding a bit more scatter, a bit more diversity in the galaxy properties at this scale. But qualitatively speaking, we find similar results. So the point is, the smallest dwarfs remain cuspy. And so what this means is, if you're interested in sort of testing robustly this prediction that you think halos at some point should be pretty cuspy. It's the tiny galaxies are the ones you want to look at, and typically it's sort of 1 million solar masses or so, dwarf spheroidal type systems. The problem is that these tiny galaxies are dispersion supported. We don't have rotation curves for them, and they are notoriously hard to use to extract detailed density profiles. One of the reasons it's hard to do this is because typically you only have line of sight velocities to these things, and there is a notorious degeneracy between the velocity dispersion anisotropy beta and observed properties like the line of sight velocity dispersion. So this is the relevant equation. And so there's degeneracies with things like the log slope of the tracer profile, which you don't know, and also this beta parameter, which is how you balance radial velocity dispersion versus tangential velocity dispersion. So it's really hard to extract a detailed density profile. But it turns out that there's one thing that you can extract, and that's the mass at one specific radius. If you take the relevant equation and you fix the observable, it turns out that you can write this in an invertible form such that the thing you're integrating over doesn't depend on big R. So you create it in a way that's invertible such that if you fix the observable, the integrand must be the same for all beta. And when you do this, you can show the following, that the mass at some radius for any beta minus the mass at some radius for beta equals 0 equals this function. And you notice that this function goes to 0 sometimes. So there's some radius where this function goes to 0. That means it doesn't matter what beta is. And it turns out that that radius is where the log slope of the density profile is -3. So if you have a tracer profile that at some point over the tracer, the log slope is -3, there should be some radius where you can determine the mass independent of beta. And this is what Joe Wolf did in 2010. The other thing that's kind of nice is R -3 is very close to the 3D half-light radius, so it's easy to use. And so that's why people quote the half-light mass for these systems, because the log slope of -3 is where this happens. And here's the formula. This is the formula that Joe derived, and it's very easy to use. And this is the formula that people use typically when you talk about the too big to fail problem. That's why every galaxy has one point, and you plot it at the radius where the log slope is roughly -3. And in principle, that's all you know. You just know that at that radius, that's what the mass is, but you don't know what it is otherwise. So we still don't know the log slope, but at least we know an overall density or overall mass. So these days, like I said, we're starting to be able to measure velocity dispersion in the plane of the sky. And there's a nice pair of papers by Massari et al. Involving Amina Helmi, where they're using combined observations from HST and then Gaia to sort of begin to measure internal proper motions of these systems. And so on the plane of the sky, typically what you do is you measure a radial, so this is the plane of the sky, you measure velocity dispersion in the radial direction and a velocity dispersion in the tangential direction, and so you have these two components that you can play with. So let's focus first on the radial velocity dispersion. That follows this equation up here, and you can play the same trick. So you massage it in such a way that it's invertible, and when you do that, you can show this, which is analogous to what I showed you before. Unfortunately, this is sad, because this does not go to 0, obviously, anywhere, and depends on beta, which is the thing you're trying to eliminate. So that didn't work. And I don't know if Alex started with this one or not, but anyway, no magic radius in that direction. But fortunately, in the other direction, there is a magic radius. Again, you play the same trick, and what you find is you get this. So now the magic radius is where the log slope is -2, and not where it's -3. So you get a different radius. So that's kind of fun. And this allows you to derive this mass estimator. And so this mass estimator is the radius where the log slope is -2, which happens to be about 3/5 the half-light radius. All the models kind of go through the same point at that place. And the mass you get is this, and the circular velocity at that point is √2 times the tangential velocity dispersion. So that's kind of neat. So now what we do, we have this formula, very little work, and now you can apply it to data. The error bars are still big, but this is kind of what it looks like when you play the game. So here is the square. These guys are Draco, and this is Sculptor. So the errors on the line of sight velocities are very, very small. We have lots of stars. And these are the Wolf masses at the 3D half-light radius. But now we have this inner mass point. And you can say, as of now, NFW looks great. In fact, I mean, the error, it's kind of lucky if you believe the error bars, but it goes like right through the middle of this particular point, and this one, the error is big. And I think, basically we've estimated that if you can shrink the error bars by about a factor of 3, which I think should be possible in the lifetime of Gaia, you can start placing constraints on core radii at that radius. And again, you can do this without doing really complicated genes modeling. You just have these masses that you can start playing around with. So if you're thinking about doing proper motion measurements and you don't want to do a lot of genes modeling to interpret them, I encourage you to use this mass estimator because it's easy. OK, so that's it. So the summary of this is that we've derived this new mass estimator. It's kind of like the Wolf et al. Mass estimator, just at a different radius. It's just as easy to use. And as of now, both Draco and Sculptor are consistent with cuspy NFW halos. But with more data, maybe we can test whether or not there's a substantial core. Thank you.
Questions? We'll start with somebody different first.
So are we in a position to estimate beta?
Yeah. So if you just take the velocity dispersions as measured, it's not really beta because it's slightly different. It's not in 3D, but it's in these projected dimensions. But if you just treat it that way, it's close to basically 0. It's close to the kind of simple one. And all these mass estimators are consistent. That is, if you take, I didn't show it, but if in this line, if you look at beta equals 0, and then you put the Wolf mass on this, it also runs right through the beta equals 0 line roughly. So. What do the models predict? Sorry? No. No, this is observed. So you observe the tangential and you observe the line of sight and you assume that that's kind of like beta and you do the ratio and it's about. Yeah. We wrote a paper where we tested these formulas and I don't, with the fire sims, and I'm trying to remember, Sandy, if we even measured beta. I don't think we did. We will do that.
So we did actually look at beta a little bit in one of Kareem's papers. And it was mildly positive. It was
mildly positive.
0.1,
okay.
0.2, 0.3.
Was that a George-Toroidal scale or?
Yeah.
Okay.
Following up on that question, I mean, maybe this is as much philosophical as it is practical, but if we're measuring beta in principle as a function of R, I mean, do you have thoughts about doing this versus just anchoring the 2 points at the density versus, then we can actually, I mean, the usual thing that makes us afraid of genes modeling is not knowing beta, but if we're measuring beta.
Well, the thing is you're kind of measuring an average beta. So the thing about this derivation is it's true even if beta changes as a function of radius for any beta profile.
We could be in a position to measure that.
You could, but it's in projection. So you're taking projected information. I mean, you're right. I'm not saying that, it could be that you just do it brute force. But what you're measuring is this projected thing, and you're comparing that to the 3-dimensional radial velocity. And so the line of sight is not radial.
Right.
So there might be some way to sort of, do that deconvolution. Yeah.
Any other questions before we move on? No? Okay, let's thank James one more time.